We're going to continue our discussion of the planetary. It's not a good sign. I can spell. Planetary energy balance, part 2. So we're sort of talking about all sorts of things related to what maintains the temperature of a planet. Like, what are the factors that basically keep the temperature on Earth in a habitable range, with some discussion here and there of like what's happened at on other planets. And the reading that goes along with this is pages 43 to 46, and so you can skip a page there, 48 to 55, from the Camperol book. We're in the readings that you've got are from the second edition. There's a third edition, and it didn't really change too much. Okay, so the main items that are relevant for thinking about the temperature at the surface, we're going to list here. So the surface temperature is a function of, this is a bit of review, solar flux, so how much energy is arriving at the planet, reflectivity, and we've been talking about albedo. We're going to abbreviate that A, which on Earth is currently around 30%. So roughly 30% of the sun's energy just bounces off the Earth at the same wavelengths that it was coming in at. The greenhouse effect, we're going to talk in more detail today about that, how that works, and how that's an important part of the keeping the temperature on Earth habitable at the moment. And then, so these are the main three, and I'm just going to put in here because there are more smaller things. So, for example, and this is something we'll be talking about later in the class, but heat is also coming up from below. So we'll call that geologic heat. But in terms of the fluxes that we're talking about here, it's very small. So the solar flux was, in the order of 1,000 watts per meter squared, and the geothermal heat coming out from below is more like 1/100th of a watt per meter squared. So we can neglect that for the purposes of the short-term energy balances that we're working with here. Okay, so I'm going to start with a bit of a review of the work that we did in class. Depending on when you're watching this, it's possible that this is going to be something we do soon, but it's worth going over again. So we're going to refer to temperature T sub E, which is the effective, it's actually as a name, the effective radiating temperature of Earth. So what does that mean? So if you want to think of it kind of, basically you could look at this and be like, it's the temperature of the surface of the Earth. But it has a bit of a more specific meaning, which is that it's the temperature of a black body radiating the same amount of energy as Earth. So it's pretty close, since the Earth is more or less, acts like a black body with some small variations. For example, like plants absorb certain wavelengths of light. The greenhouse gases absorb certain wavelengths. So it's, if you look at an actual curve, and this is just an aside, but like the theoretical black body curve might look like something like this, no bump there, and then the actual one kind of, it's a little bit more like that, but more or less like the integral of that curve is going to be the same. So we can calculate this temperature. This is a slightly different version than we did in class, so it's worth going through this just to sort of see it more in terms of this balance. So we're going to balance energy emitted by Earth. So this is the energy coming out, and it's in the infrared spectrum. So the energy is going to be like the energy flux, which is some amount of energy per meter squared, times an area. Oops, don't seem to be very good at spelling today. So the meters squared will cancel out, and we'll just have like total energy. So that flux we saw in the previous lecture, according to this Stefan Boltzmann relationship, is equal to the temperature, this effective radiating temperature, to the fourth power times some constant. And we multiply that by the spherical area of the surface of the Earth, which is 4 pi r radius of the Earth there, squared. And we're going to balance that with the energy absorbed let's say from the sun, which is going to be the solar flux times the area, minus the reflectance times the area. So we're going to we can just right away just remove the stuff that bounces back. So that's going to be solar flux. We're going to abbreviate S. And as I described in class, the sun, because it's so far away, the Earth, the energy that the three-dimensional Earth receives is the same as a disk, a circular disk that has the same radius. So at different latitudes, the energy is coming in at different angles, but that can be sort of that just balances out if you can just simplify it as an area. So solar flux times pi r squared minus the solar flux times the albedo. This is a times pi r squared. And that simplifies down to solar flux pi r squared times 1 minus the albedo. So let's call this equation 1 up here and this equation 2. Combining these, we get that constant from the Stefan-Boltzmann relationships, sigma, times the temperature at the surface, approximately, is equal to the solar flux divided by 4 times 1 minus the albedo. And so using this equation, we can calculate, and we did in class, calculate the temperature of the Earth that we'd expect in a very simple model where there's no atmosphere, but we are accounting for albedo. And if you use this constant here from physics, using the albedo that we gave, 30%, and the solar flux, which is measured from satellites, so all those things are pretty, they're at the moment anyway constants. You get a temperature of minus 18 degrees Celsius, which is around 33 degrees colder than observed. And this calculation is an important one because it tells us that the overall greenhouse effect magnitude equals 33 degrees. So unless you can think of some other reason why this temperature, something else that affects the planetary temperature to any significant extent, it must be the greenhouse effect. That's kind of the only thing left. So that's a very useful constraint because we've approached this from a perspective where we're not doing any fancy computer modeling or anything like that. So it's a way of, we can use this number to validate different approaches that we might take. So we could take a model where we actually account for all the different layers of the atmosphere and the physics of molecules that are being bombarded by solar radiation and try to get into real, and run it on a supercomputer for weeks, right? But this number is critical. It's like, okay, well, if we're doing it right, it should end up around, at this number. So let's talk for a moment. So this calculation we just did, energy, it involved this energy balance assumption. It's worth discussing for a moment. So that is that we said the energy arriving from the sun is equal to the energy that's radiating off the Earth, and that's how we set this up. And of course, we know because the Earth is getting warmer, right? So this is not actually perfectly true. And it's worth kind of considering this for a moment. It's not perfectly true. The planet is warming. We're measuring that. It's warming by around 0.02 degrees per year. So we're thinking about, okay, is this calculation, is this approach, still valid, even though we know that it's not exactly balanced. But since it's such a small change, we kind of go ahead and can make this kind of calculation. Nothing in this calculation. So if we think that, okay, the reason it's not balanced is because of some perturbation right now, where we're putting more greenhouse gases into the atmosphere. But there's nothing in this calculation that has anything to do with that, right? The solar flux, the albedo, the solar a constant from thermodynamics, like those things don't affect this. So this calculation applies as much to the time before humans were influencing the climate to such a degree. So you could think of it that way if you want. Okay, let's dive into the greenhouse effect. In more detail. Okay, the atmosphere is mostly composed of gases that are not greenhouse gases. Mostly, let's say it's around 90% nitrogen and oxygen, and there's a bunch of other gases too. These are transparent to electromagnetic waves. So just like visible light, when it goes through clear glass, it comes out the other side just as bright. The glass doesn't warm up. That's what we mean by transparent. The same thing occurs in wavelengths that we don't see. If you have a tank of oxygen or nitrogen or a combination, and you shine a light through it, the same amount of light energy comes out the other side as you project it in. And same thing with infrared light or infrared energy. Okay, and this has to do with the symmetry of these molecules. Cause this. So the waves don't affect the waves in the wavelengths of energy that are coming from the sun. They don't disturb the nitrogen and the oxygen molecules. They don't resonate. So there are gases where this is different. So the main greenhouse gases, we'll list them. Oops. The biggest one, which actually causes the most of the greenhouse effect, is water vapor, which makes up about, depending on where you are, if you're in the desert or the tropics or the equator, it matters a lot, but it's somewhere between basically 0 and 4% of the atmosphere. And it contributes around 3/4 of that greenhouse effect, that 33 degrees. And we will shortly talk about why we focus so much more on carbon dioxide than on water vapor, even though the water vapor is the thing that actually makes, if you just look at molecules in a tank, in a test chamber, water vapor is more powerful. So CO2 makes up about 0.04. Actually, that's not quite. Take back what I just said a moment ago. Because look at CO2. It makes up. It's a smaller. There's a much smaller amount of it, but it still has about roughly a quarter of the greenhouse warming. So apparently, a molecule by molecule basis, CO2 is stronger, but there's a lot less of it. But overall, there's a lot more water vapor out there, and it has a bigger effect. And the same thing kind of goes for these other ones. There's very little methane. Other ones include ozone, freon. These all have an effect, a greenhouse effect, but the effect isn't as big as the major players here are water vapor and CO2. So why do these absorb infrared radiation? We talked about in a previous lecture how the detector that's used, if we met in order to measure the CO2 concentrations, we use this effect. If you take a gas sample where you have a source of electromagnetic radiation, and you have some tubes, and you shine that radiation through the tubes, and one of them is just full of nitrogen, and the other one has your air sample, and then you have a detector. So you have your gun here, your light basically, and then you can compare. Okay, when the light goes through this tube, that's your reference, and then you see, okay, when there's, based on how much energy actually makes it through, that's how you can calculate the CO2 concentration. Or I guess it would be actually the concentration of all the different greenhouse gases in there together. So why does this happen? Why do some of these molecules have that effect? And short answer, you can read more in the reading, but sorry. So infrared radiation, there's a number of different mechanisms that the molecules in different wavelengths at which they operate. So these are a couple of the main players. So infrared radiation with a wavelength that's greater than 12 microns, it causes water vapor to rotate so the water, having the sort of it's got this asymmetry, and because of the properties, when you hit it with the right wavelengths, anything bigger than 12, and this effect goes into the microwave range, and that's actually why that's how your microwave works. You send electromagnetic radiation in the right wavelengths, microwaves, and it causes, when it hits the molecule, it sends it spinning, which is a sort of it's a kinetic, it's at a molecular level, it's kinetic energy. So it gets the molecules moving more, which is what we know of as temperature. It's converting the energy from the wave, from the photon, when it hits the water molecule, it disappears and the molecule starts moving. So we haven't lost any energy, we've just converted it. So that's a big one. So for water vapor, electromagnetic radiation with anything larger than around 12 is going to get absorbed by water vapor. And for CO2, and there's other ways that for both of these are just some examples. Let's be clear about that. Examples. Just so you kind of get the sense of this. So carbon dioxide has what's called a bending mode of vibration. That absorbs electromagnetic radiation that has a wavelength around 15 microns. So basically, for the CO2, you have oxygen, carbon, oxygen. This can kind of oscillate, kind of back and forth like that, and photons that are coming in with a wavelength of about 15 microns cause this to happen, right? And that's just another way of producing thermal energy or converting electromagnetic radiation into thermal energy. And there's also absorption at many other wavelengths. Okay, so these are just some examples, some main examples of what's happening at more of a molecular level when these wavelengths of light are traveling through a gas that has water or CO2 in it. Okay, the next topic we're going to look at here is looking a little bit more in detail at albedo and the effect of clouds. So we've just so far just said, okay, albedo is around, its reflectance, it's around 0.3 for the Earth currently. But it turns out that it's mainly clouds that dominate the albedo. So, let's quantify that. So Earth's albedo around 0.3 currently. Would be, if we didn't have clouds, it'd be around 0.1 without clouds. So 2/3 of the albedo is due to clouds at the moment. And clouds are kind of tricky. They absorb, at night, they absorb outgoing infrared radiation. So at nighttime, the clouds actually act as they help with the greenhouse effect. So the effect of clouds is both, depending where and when, is both cooling and heating. And clouds, it turns out clouds are one of the biggest unknowns in climate models, projecting what's going to happen as greenhouse gases increase. And that's in large part because the effect of clouds depends on their location. If they're higher or lower in the atmosphere in particular is important. And the clouds can move around, they have different shapes, and they're a big unknown in terms of predicting what's going to happen. So let's, during the day, you could think, let's just draw a little diagram. So in the day, this is the sort of the simplest version of this. In the day, the sunlight bounces off, okay? And this is this albedo issue. But at night, the sun's not there. You can put the moon out, I guess. At night, here's the ground. The cloud causes, it gets in the way of the infrared radiation escaping into space. And you might have noticed this, right? Cloudy day, when it's a cloudy night, it will be warmer than a really clear night. And same thing, right? If it's a cloudy day, it's not as warm typically as it would be if it was sunny. So let's summarize. So make some space. We're going to draw a big diagram here that captures the what's keeping track of all the energy. So we're going to start with the sun. So energy is coming from the sun, incoming, and we're going to just choose arbitrarily. We're going to say there's 100 units of energy coming in from the sun. Okay, so some of that energy makes it down to Earth's surface. This is the ground. It's about half, so about 45 units of energy make it to the ground, where they're absorbed. For example, plants doing photosynthesis, the ground getting warmer. So this line hitting the ground is part of this absorbed energy. Some of that, the rest of it gets, different things happen. Some of it we were just talking about, some of it comes in and is reflected back. So we could just label this reflected. So this is the albedo effect of the clouds that we were just talking about. That would be around 25 of those 100 units. And then we were saying there's also some of the albedo effect is the surface. For example, ice, white daisies, etc. There is some around 5, not as much as the clouds. That's reflected. And okay, what are we missing here? 45 plus 25, we've got 75. So the remainder is absorbed in the atmosphere. So we've been focusing on how infrared wavelengths are absorbed by molecules in the greenhouse effect, but there is some absorption of at the shorter wavelength radiation as well. Okay, so this is sort of one aspect of this balance. Okay, and we're getting out. You can see we're getting out around 30 reflected. So that's that term when we say the albedo is 30. That's the 30 there, and we're going to balance this. Okay, so some other things are happening where 70 more is going to come out. So let's look at that. So, okay, basically, okay, we've already accounted for this 30. So some of this, what happens to this absorbed energy in the ground? Okay, so, or on the Earth's surface, I should say better. So Earth warms up, and if you've there's an effect called thermals, right? The ground gets warm, it warms up the air above it, and that air rises up. Okay, so that's a way that this absorbed energy from the sun heads back in the direction of leaving the planet, but not nearly as much as energy is captured by evaporation. 24. Okay, so we'll indicate a cloud here as well. So what's going on here with the evaporation? Okay, so the heat is being used to convert liquid water or ice into water vapor. And that is a reaction that absorbs energy. So the water vapor, just by its nature, is carrying that energy and enters the atmosphere. And later, when it condenses into clouds, it releases that energy. So it's a way of moving. It's a major way that energy is moved from the ground surface into the atmosphere. So that together, that energy, that heat energy, right? Anything with a temperature is in a mass is radiating infrared. So that we can add those together, 29, and this infrared energy is escapes. Okay, another thing that happens, and so now we're getting to the greenhouse effect, is simply that, so this radiated energy, I'll draw another cloud. It simply radiates because of the physics that we talked about before. And this number might surprise you, 100. Reflected down from, and this is not just clouds, but let's call it clouds and gas. Okay, so that energy radiates into the atmosphere, and then it's absorbed, as we've been talking about, by the greenhouse effect. It just warms up the air, right? And then that warm air radiates back. It radiates in all directions. It radiates both up and down. The numbers here are 12 and 88. So we'll label this the greenhouse effect. Okay, this is another way of looking at why does the presence of an atmosphere change the surface temperature? It's partly because you have this energy just kind of bouncing back and forth and keeping this area at a warmer temperature before it escapes. And a little bit of this radiation from the surface escapes, around 4. All right, so we could sum up these. And this is the infrared radiation that's leaving. And let's see, 29 plus 4 is 33, plus 12, 45. So we're missing something. Right, because this in and out should be balanced. So here's what we're missing. So some of this energy was absorbed directly by the atmosphere. And let's see, we had 100 coming in and went into 50, 25. So there's another 25, right, that was absorbed. And that comes out here, 25. So that should equal 70. Right there at 35. Just going to check my math here. So 54, 58, 70. Okay. So what are the key points from this? Total energy, which I'm just abbreviating E, absorbed by the surface is 133. Right? It's 45 plus this 88. Which is, this is twice the energy from the sun, if we roughly. So that's the greenhouse effect, right? So energy is absorbed. How is that possible? It's absorbed and re-emitted by the atmosphere multiple times. So it's this kind of back and forth. The effect of just kind of keeping this energy in this area before it eventually escapes. So another key point here is the importance of evaporation. Right? So half of this energy coming in from the sun, roughly, is carried up by this process where the water molecules absorb that energy as they turn into a gas. And that that's partly the reason why, that's part of this calculation of the effect of clouds, right? You can see how important they are in many different ways here, including how they form as a result of the condensation. Where they form, they're bringing the heat that's being carried out from the ground. So let's just write that down. So this is the evaporation being energy used to evaporate and then that energy is released at higher altitudes. When condensation occurs. And of course, this is a simplified model, right? So it's not the case that all of that energy just bypasses the greenhouse effect. So these are mixed together, right? So some of that, and once the energy is is thermal energy in the atmosphere, it's going to, some of it's going to go into space, some of it's going to bounce down towards the Earth again. But drawing it out like this as sort of a separate thing might be useful for just trying to keep track of the overall system. Okay, so let's talk next about, and this will be the final topic, what are the important feedbacks that are part of this system? So the first one is related to what we were just talking about, water vapor feedback. So if the temperature if it gets colder, if the temperature goes down, that causes condensation. The air can't hold as much water vapor in it, so it condenses. We get rain or snow. And so when there's less water vapor in the atmosphere after the raining and the snowing, there's going to be less greenhouse effect. All right, let's draw that out. So, okay, we have the temperature of, let's say, atmospheric temperature. Okay, if it goes down, the amount of water vapor goes down. So is that a plus or a minus? Think about that pause the video and think that through. What am I going to put a plus or a minus sign here? Okay, that is a positive, right? So one thing goes down, it causes the other to go down. I could have talked through this the opposite way and said, okay, if temperature goes up, then I'd say condensation goes up. Okay, that's what we mean by a positive feedback. Okay, so that increases the greenhouse effect. Or sorry, if in this case, okay, if we have more water vapor, we have more greenhouse effect. If we're starting with this thing, thinking of this as the temperature going down, in that case, temperature goes down, less water vapor, less greenhouse effect. It's still positive. And okay, if there's less greenhouse effect, there's going to be less atmospheric temperature, right? temperature is going to go down. So that overall is a positive feedback loop. So this is a positive feedback loop. And like all positive feedback loops, we can think through it in terms of things going up or things going down. But in any case, it's a runaway effect, right? And you could start anywhere in here, right? Like these diagrams. Let's say that for some reason we didn't have a lot of water vapor in the atmosphere. Okay, so that would cause less greenhouse effects, which would cause the temperature to decrease, right? Which would cause even less water vapor to be in the atmosphere, and so forth. And from modeling of this is expected to amplify the temperature, any temperature perturbation. So if we change the temperature because we add a bunch of CO2 into the atmosphere, this magnifies that by a factor of around 2. Okay, so if for some reason, for example, putting more carbon in the atmosphere, we raise the temperature 1 degree just based on the carbon, that warmer atmosphere will hold enough more water to raise the temperature another degree. So that's what we mean by a factor of 2. If we were to increase the atmospheric temperature 2 degrees based just on the effect of CO2, the total actual temperature change would be 4 degrees. Okay, the next feedback I'm going to talk about is related to snow and ice, albedo. So this one, we've talked about a version of this before when we talked about the snowball Earth. So if, in this case, if the temperature goes up, ice melts, the albedo goes down, so there's less reflectance, which is going to cause the temperature to go up. Okay, so let's just call atmospheric temperature T. Okay, so this causes, maybe you want to pause the video and see if you can write these out yourself. Temperature, so temperature goes up, less ice cover. That's negative. Less ice cover, what effect does that have on albedo? Less ice cover, less albedo, right? Less albedo, higher temperature. I screwed this up. Less ice cover, less albedo. That's a positive, right? So altogether, this is a positive feedback. And so this is the same loop as snowball Earth. So we looked at this previously where we talked about how this could go the other way. If it gets colder, temperature goes down, we get more glaciers, more ice. That makes the more ice, more albedo, more reflective, so the Earth gets less energy from the sun. Earth is more reflective, that makes it colder, okay, and it loops around until the whole planet is covered in ice. That's what we meant by the snowball Earth hypothesis. But at the moment, we're more concerned with the other direction. And so so far we've talked about two feedbacks that can destabilize the planet. So there's got to be, since the planet temperature, surface temperature, seems to be pretty stable overall, there's obviously negative feedback going on here as well. And the main one, which is super important, is this maybe something we've sort of been assuming or been talking about all along, but we haven't looked at it in terms of a feedback. And that's just simply that when it's warmer, more infrared radiation is created, right? That's the Stefan Boltzmann relationship to the power of 4, right? So if the temperature increases, the amount of infrared radiation goes up. And so if we're blasting more energy into space, that is going to bring the temperature down. So overall, it's a stabilizing loop. So we'll just write that out. If temperature goes up, more energy is lost to space. And the opposite as well, right? If the temperature goes down, we're not going to shine as brightly, which is going to keep more energy in the Earth surface, which will bring the temperature back up. So this has worked on our planet so far, but this could potentially fail, and this is what we think happened on Venus. So for example, if you got too many clouds, there's something called the runaway greenhouse. So it gets a little bit messy when you consider this kind of mixing with this, right? So if the temperature increases, overall we're at the moment, the way things are working, we're radiating that energy out into space. But if this took over, where the temperature increase actually created such a blanket of atmosphere, this effect could overtake this one. This is part of the explanation theory for why Venus is so hot. So this isn't something that atmospheric scientists are particularly worried about these days, but it's sort of on when you're considering the fate of planets, this is a possibility. Yeah, so these three, let's underline this one. These are the three major feedbacks that are to think about in terms of the stability of the climate.